What are complex numbers? Before we define complex numbers, let's solve this question. When you have x squared equal to 49, and we ask about the solution of this equation, we'll say x is equal plus or minus square root 49, which will be equal to plus or minus 7. Okay, what about x squared is equal negative 49? We'll say x is equal plus or minus square root of negative 49. So you can break it into plus or minus square root 49 times square root of negative 1. It's equal to plus or minus 7 times square root of negative 1. What is the square root of negative 1? What is the number if you multiply it by itself, you get negative 1? Nothing. So we'll just imagine that we have a variable called I squared equal negative 1. If we have this variable, the problem is going to be solved, because if we have I squared equal negative 1, it means I is equal to square root of negative 1. And in this case, it's solved. All right, so we are going to assume that there is a imaginary number, which I squared equal negative 1. In this case, the solution of the example here, x will be equal to plus or minus 7, and this one we'll call it I, and that will be the solution. So I is the imaginary number, which is equal to square root of negative 1. It means that I squared will be equal to negative 1. Well, what about I cubed? I cubed will be equal I squared times I, which is equal to I squared is equal to negative 1, and I, negative I. What about I power 4? Means I squared times I squared. I squared is negative 1, I squared is negative 1, so it will be equal to positive 1. We'll observe something here. What about if we have a circle and we know that we start from this point, it's 1 at this point. We observe that if you have 180 degrees, you reach here negative 1. So negative 1 corresponding to I squared. So this is actually equal I squared, negative 1. So I squared rotating by 180 degrees in this direction. So if you only want to have only I, you will be here. And if you look for I cubed is equal negative I, that will be the point, negative I. And the I power 4, you did 4 90 degrees, will be equal positive 1, you go back here, which is equal to I4. So you can look for I like rotating by 90 degrees. That's another interpretation for I. Okay. How can you represent the imaginary number on the Cartesian coordinate? Well, let's have x-axis, y-axis. We used to x-axis represent the real number. So we'll say that that's the real number. You have 0, 1, 2, 3, 4. And that's the negative side, negative 1, negative 2, negative 3, negative 4, and so on. The vertical axis now will represent the imaginary number. The imaginary number this number that starts with I, like when we did last time. So when we solve this problem, we say x is equal plus or minus 7i. So 7i is called imaginary number. So imaginary number has I. You can say 7i, 5i, 6i. It could be negative, negative 5i, negative 6i, and so on. So the vertical axis, that's I, 2i, 3i, 4i, and here we have negative I, negative 2i, negative 3i, negative 4i, and so on. So x-axis now represent real numbers, and the vertical axis represent imaginary number. If you have a number that has both real and imaginary, how do you write it? Well, when you say z equal to 3 plus 4i, that's the real part, and 4i, that's the imaginary part. So the real part 3 will be represented along x-axis. So we look here, we have x is equal to 3, 1, 2, 3, you have 3 here, and 4i, 1, 2, 3, 4i. So if you make broken line at 4i and broken line at 3, that's the point. And if you connect the origin by the point, so this is the point 3, 4i, and that will represent the complex number. So z is called complex number. So complex number contains two parts, real part and imaginary part. That's z, and that's how we represent it in the rectangular form. So in general, z is equal a plus bi. That's the real number, and that's the imaginary number, and this one we'll call it complex number. And this representation in rectangular form or Cartesian. Okay, there is another way to represent this. What is the length of this vector z? The length only. We can use Pythagorean. The length of this is equal 3, and the length of the vertical is equal 4. So let's just do it here. So we have rectangle 3 and 4. That's A, and that's B, and that's C. Don't forget, Z is equal A plus BI. That's the complex number. The length Z will be equal A square plus B square square root, and you can call it R. That means the absolute value of Z, of the complex number. What about the angle theta? Theta will be equal to tan minus 1, the imaginary part, which is B, divided by A. So that's the angle. So we can represent the complex number in another way. We can say that Z is equal to the length R and the angle theta. And theta could be written in degrees or in radian. In our example, when we say that Z is equal 3 plus 4i, that's the rectangular form, and in this form we are, or this form we can call it, if you wish, polar form. Polar form can be represented by the length of the complex number, which is R. In this case, since it's equal 5, we just we do A square plus B square square root. A in this case is equal 3, B is equal 4, so you have 3 square plus 4 square, which is equal 5. So the length is equal 5. What about the angle theta? Theta is equal to tan minus 1 B over A. So I'll say theta is equal 10 minus 1, 4 over 3. So what is the angle? 4 over 3. Well, if we use the calculator, let me just calculate here using the calculator. That would be equal to 53.13, just let's round the number. So 53 degree. So that's how you represent in the complex number in polar form. So let's just do summary of what we did. Z is equal A plus B. That's the complex number and represented in rectangular form. And by the way, in some textbook will be written like A plus JB, both they are fine. And in polar form, you can write Z is equal R and angle theta, and where R is equal to absolute value of Z, A square plus B square, and theta is equal to 10 minus 1 B over A. So that's how we convert from Cartesian to polar. Can you do the opposite? Yes, you can. Yes, you can. To do that, let me just show you something here. That's complex number. That's A, and that's B, and that's the angle theta, and that's R, which equal the absolute value of Z. We say Z is equal to A plus BI. All right. If this is R, we call it R here, which is absolute value of Z. So what is A? If you make a resolution along this one, you can say A is equal to R cosine theta. So A is equal R cosine theta. What about B? Well, B will be equal R sine theta. B is equal R sine theta. Okay, so if you have the complex number expressed in polar form, you can convert it to Cartesian form. Let's now try to define the polar form in different form. There is something called Euler. Euler identity, and it's important to deal with complex number. Okay. We know that if you have complex number A plus BI, it can be expressed R an angle theta, and we know that A is equal to R cosine theta and B is equal R sine theta. So the complex number can be written R cosine theta plus B, which is equal to R sine theta I. That's the real part A, and that's the imaginary part B. Well, Euler said that if you have, let's say, R equal 1, special case, if R equal 1. So in this case, what is Z? Will be equal cosine theta plus sine theta I, or you can use the other form, put J in there. That represents the angle theta actually, right? Like you have a rectangle, and this is equal 1, and you got theta, so that's cosine theta, and that's sine theta. So that's actually represent this complex number. Euler said you can express this in different form. If you do the polar form, as we said before, say 1 and angle theta. Euler said we can write it like exponential form, E power I theta. that will represent this. So e power I theta is equal to cosine theta plus j sine theta. That's Euler identity. So now the example that we did before, and we converted from Cartesian to polar, we said it's equal 5 and the angle 53. That can be written like that. Z, which is equal 5 and angle 53, will be written using Euler identity. 5, that's the length, and the angle, this angle, will be e to the power of I 53. You can say it j, it's okay, I say it j, or you can write it 5 e 53 I. So let's just take one simple example. Let's say that you have a complex number, and this complex number expressed as 5.39 e to the power of j 21.8 degree. So what is that? That's a complex number expressed in polar form, and we used the Euler identity. If you want to convert this number, the complex number, into complex number in rectangular form, so what you'll do, remember that will be your r, 5.39, and that would be your angle theta, the one after j, will be equal to 21.8 degree. In this case, if you sketch a triangle, just to make it easy to understand, this r, the hypotenuse of the right triangle, 5.39, and the angle is 21.8. So this is the way that's expressed in polar form. To convert it to Cartesian, you'll say z is equal to a plus jb. I'm using now j. What's a? R cosine theta. What's r? 5.39. It's equal 5.39 times cosine, and the angle 21.8. So when we'll do that, we'll find the value for a. It will be equal to 5, around 5. What about b? How we find b? B is equal r sine theta, because this is your r, this is your theta. That will be r cosine theta, which is equal a, and the vertical line will be r sine theta, which is equal b. So b is equal r sine theta, and r is equal 5.39. It's equal 5.39 times sine theta 21.8. That will be equal to 2. All right. So this number could be represented as the real is equal 5, the image equal 2, j2. It's the same as was expressed in polar form, 5.39 e to the power of j 21.8 degree. So that's how you, well, before we move to the next point, try first stop the video and do these practice questions. You have here in yellow the problem, and you have here in red the answer. So check yourself before we move to the second point. We'll go back. Okay, after you practice how to convert complex numbers from polar form to rectangular form, and from rectangular form to complex form, let's now start how to perform the basic operations on complex number. Assume that we have two complex numbers, z1 and z2, and they are given here in both forms. Let's start with the first basic operation, addition of complex number. So we want to find z1 plus z2. When you add the two complex number, you look for the first one and the second one. Add real and real. The real of the first one is 3 and the real of the second 2. So you add the real. Plus j, you add the imaginary part, you have 2, and 4 will be 2 plus 4. So the answer will be 5 plus j6. The same thing for subtraction. If you have to perform subtraction, and let's say that you want to find z1 minus z2. Let me write z1. z1 is equal 3 plus j2, and you want to subtract it from z2. 2 plus j4. So subtract real from real. Will be 3 minus 2, and then you have plus j, and you have 2 minus 4. That will be equal to 1 minus j2. Okay. The third basic operation, multiplication. We want to multiply z1 times z2. When we go back to z1 and z2, you will observe it's expressed in both Cartesian and polar. When you multiply, it's easier to use the polar form. Let's just take a copy of z1 and z2. So to perform the multiplication, I'm going to use the polar form, this one and this one. So I'll say z1, z2 equal to 3.6 e to the power of j, missing j here, 33.7, that's z1, time z2, 4.47 e to the power of j, 63.4. So when you multiply, first multiply the length, this number. So it will be 3.6 times 4.47. And what about the angle? You have e to the power of j, 33.7, and j, 63.4. You add. When you're multiplying the exponential, you add. Will be 33.7 plus 63.4. Then when you multiply, you will get 16.12 e to the power of j, when we are adding the angle, will be equal to 97.1. So that will be the answer, and you can convert it to in Cartesian form if you like. Will be equal to minus 2 plus j16. So what we're saying here, when you multiply z1 times z2, z1 is defined as r1 angle theta 1, that's z1, and z2 r2 ej theta 2, that's z2. So when you multiply r1 and r2, and the angle, we write e, j, and we add both, theta 1 plus theta 2. So that's the way to multiply. Okay. What about divide? So the fourth operation, division. I want to divide z1 over z2. Again, it's better to use polar form when we divide. I'll write again z1 over z2. z1 was equal to 3.6 e to the power of j, 33.7, and z2 was equal to 4.47 e to the power of j, 63.4. So when you divide the magnitude of each, 3.6 divided by 4.47, and then you write e, j, the top angle, it's 33.7 minus the angle on the bottom, 63.4. So what we get 0.806 e to the power of minus j 29.75. And if you wish to convert it to rectangular form, it will be equal to 0.7 minus j 0.4. And you can test yourself how to convert from polar form to Cartesian form as we did in the previous lecture. Well, let's move. We did the division. All right. Now let's do how to find 1 over z. That's reciprocal. Let's say that z that we have is z1. We'll take the same value that we used, so when you review you have only 2 values to check. z1, it was given as 3 plus j2, and in polar form was given at 3.6 e j 33.7, and it's required to find the reciprocal, which means 1 over z. So how to define 1 over z? 1 over z, it's very easy, because if you write it like that, will be 1 over 3.6 ej 33.7. You can consider 1 as 1 and the angle is 0, right? So it'll be like we're making division. So 1 over 3.6, that will be the magnitude, and the angle will have j 0 minus, will be minus j 33.7. So to find 1 over z, you just flip this number and put negative sign in front of this angle, and you get it. So let's see the simplification of it. That would be equal to 0.227 e to the power of minus j 33.7. You can convert it, of course, to Cartesian form or rectangular form. Will be equal to 0.2308 minus j 0.1538. Let's move to the operation number 6. Will be square root. How to find square root? We want to find the square root of z1. z1 was given. I will use again the polar form. That let's just remember where okay, that's equal 3.6 e to the power of j 33.7. So it means square root means power half. You can write the same thing here, 3.6 e to the power j 33.7, the whole power half. The magnitude will be power half, and this one exponential j 33.7 power half. 3.6 power half means square root 3.6. E to the power j o. So if you have e power n and all power m, what you'll do is say e power n m, you multiply, right? I'm doing the same thing. ag 33.7 power half will be time half, so it will be 33.7 divided by 2 when I multiply both. So the answer will be 1.9 e to the power of j will be 16.85, and if we convert it to rectangular form, be 1.817 plus j 0.55, and that would be the answer. So that was how to find the square root. We'll go now for important one, the last one we're going to do, complex conjugate. What's complex conjugate? Okay, I will take z1. I will express z1 in both. I'm going to show you how to do the complex conjugate using both forms, rectangular and polar forms. z1 is equal to 3 plus j2. It's the same as 3.6 e to the power j 33.7. To get the conjugate, we'll just use the symbol. That will mean the conjugate. All what's supposed to do, write it back again by changing the sign of the imaginary number. Instead of plus, would be minus j2. If it was minus, would be positive. How we do it in the polar form, that's the magnitude, and then you flip the sign of the exponential here will be minus j 33.7. And if you want to see how it look like graphically, that's if you remember, that's the real number and that's the imaginary number. Let's say that you have number here, that's real and imaginary. So the conjugate will be reflection on x-axis, will be that. Why? Because the imaginary part here change the sign, but for the real part it's the same. So it's equivalent to reflection on x-axis. Okay. So I want you, before we move to another section, to test yourself how can you perform the operation. So let me give you some practice here and make sure that you can do it. Okay. So you have two problems here to solve to check if you understood the operations on complex numbers. You got two problems here. That's you have 40 on angle 50 plus 20 on angle negative 30 degrees, and then after you add them, you get the square root. All right. The second problem is 10 on angle negative 30 plus 3 minus j4. You add, and after that you divide on the result of the bottom here, which is 2 plus j4 times the conjugate of 3 minus j5. So this conjugate only working on this one, just to not to confuse. And you have the answer here. So try to solve and take your time and see how to do it. Now we'll just review the Euler identity, and it's really important in coming topics in introduction to signal processing. The basic one we just did previously said that e to the power of j theta is equal to cosine theta plus j sine theta. That's if you have a negative, you just choose the negative side of this one. All right. So if we take example, if we say that e to the power of j 30 degrees, what is the value of this one? It will be cosine 30 plus j sine 30. What's cosine 30? Well, cosine 30 is equal to square root of 3 over 2 plus j. What's sine 30? Is equal half. So in this case, e to the power of j theta expressed in rectangular form as you see here using the Euler formula. You can do the other way around too. So there are other things like how can you express cosine theta by itself or sine theta by itself? Let's just do that. If you have e to the power of j theta is equal to cosine theta plus j sine theta. And what about e to the power of minus j theta? That will be equal cosine minus theta plus j sine minus theta. In this case, cosine minus theta is the same as cosine theta. They are equal. And sine minus theta is equal minus sine theta. So you can minus j sine theta. So simply, now understand that ej theta equal to this, cosine theta plus j theta, and e power minus j theta equal to cosine theta minus j sine theta. Okay. What happens if we add both e j theta plus e minus j theta? If you add it, we add cosine theta with cosine theta, that will be equal to cosine theta. When you add j plus j sine theta and minus j sine theta, you get 0. So when you add, you get 2 cosine theta. If you divide by 2 both sides, you'll get cosine theta is equal to half e to the power j theta plus e to the power minus j theta. So we got a very important formula how you express cosine theta as a sum of exponential function. All right, what about if we subtract both? E j theta minus e minus j theta. Let's just do it here. E j theta minus e minus j theta equal. That would be this one minus this one. Cosine theta minus cosine theta will give 0. J sine theta minus j sine theta give 2j sine theta. So that's equal to j sine theta. So how you find sine theta? You divide by 2j both sides. So sine theta is equal to 1 over 2j e to the power of j theta minus e to the power of minus j theta. And that will be the expression for sine theta. So we got two important formula here. One for the cosine. So you add ej theta minus ej theta divided by 2. If you want to find sine the angle, you get ej theta minus e minus j theta and divided by 2j. So for example, if you want to express cosine 30 degrees, that will be equal half ej 30 plus ej minus 30 if you are using degrees. What about sine 30? That will be equal to 1 over 2j a e g 30 minus e minus g j 30. So that's how you express the cosine and sine. So that's the way that you express it. There are, of course, certain cases like, let's say, what is e j pi? You remember, I'm going to use this a g theta. What's equal? It's equal cosine pi plus j sine pi. Cosine pi is equal to what? Is equal to -1. And sine pi is equal to 0. So e j pi is equal to -1. It's a special case. Very important that we know this special case. What about if it was e minus j pi? If you put here, it will be the same because this part is equal 0. So e minus j pi, again, is equal -1. Well, let's take another special case. E to the power of j pi over 2. That will be equal to cosine pi over 2 plus j sine pi over 2. Cosine pi over 2, that's equal to 0. That's 90 degrees. Cosine 90 degrees equals 0. Sine pi over 2 is equal 1. So e j pi over 2 is equal plus j times 1 is equal j. So j is equal e power j pi over 2. What about it was negative? Negative, if you have e to the power minus j pi over 2, we can do it fast because the only thing will change the sign. So it will be equal minus j. So these are special case important that we know to help a lot. And we have here practice 3 problems. So you can solve it, convert from one form to another. So number 1 and number 2, they are given, these complex numbers are given in rectangular form. You are going to convert them to polar form, and the last one in polar form converted to Cartesian form. Okay, we're done with the complex number. Oh, thank you.